Okay, thank you very much. It is an honor and a pleasure speaking here in this session honoring Professor Frank Vecchio. And considering that a lot of work, I don't know if most, but a lot of work of Professor Vecchio is in finite element modeling of concrete structures, it's only appropriate that the saga continues with the presentation here, where I'm going to talk about finite element analysis of slabs, flat concrete slabs supported on walls. Okay, so we have, I would like to first, I don't know which screen look at, but maybe this one better. So first I would like to acknowledge my co-authors, my Dr. Graham Milligan, my former doctoral student, and my colleague Cory Zurel, who works in Waterloo and added a lot of practical comments to this work. Okay, so first the motivation. Why did we start analyzing this system? So flat slabs supported on walls. Flat slabs supported on columns are quite common and quite easy to construct, and there is a lot in the codes how to design them. The biggest problem in these slabs is probably the shear around the column and possibility of punching shear around the column. But these systems are relatively, have low stiffness, and therefore, in majority of cases, anytime you have any lateral loading on the system, you are going to construct the walls to stiffen the system. And in these walls, everybody can sort of feel that there could be a problem of punching shear, but the codes really don't address this explicitly. So nobody knows what to do with them, and are we in trouble or not when we are constructing these walls? Oh, I do have even pointing out where the punching shear could be happening. Okay, this slide is really self-explanatory. Most people in this audience know what punching shear is. It's formed by this cone, cracked cone forming around the column. This is the picture taken from the book by McGregor. Again, probably most people saw the picture already. But the codes, the code provision handle this punching shear by specifying so-called critical perimeter around the column, which here there are red lines showing that this inclined crack is modeled as a vertical sort of plane going around the column. In Europe, it's called control perimeter, by the way. But in North America, it's critical, and it's really the same thing. And here you have two critical perimeters, one according to ACI, one according to the old Euro code, EC2, and they are completely different. So, and this is for the slabs supported on columns. For the slabs supported on walls, ACI doesn't have really any recommendation when the column, rectangular column, becomes a wall. ACI 352 suggests using recommendations by Schweighofer and Collins, where basically only portion of the critical perimeter is considered around the tip or toe of the wall. And then there is an FIB model which sort of explicitly addresses this issue. But other than that, there is no more guidance of what to do with these walls that support flat slabs. So if you don't know what you are doing, then you are doing too much, just in case. And this is actually a picture taken from actual project on where the consulting engineers designed this kind of reinforcement at the end of the wall. Because they didn't have any guidance what to do, and they didn't want to have any trouble there, so they specified all this reinforcement. That is quite a lot of reinforcement, but I wouldn't blame them because there really is not much to go by. Okay, so, and also, very important part here is that there is limited experiments, very limited experiments. For many reasons, it's difficult to test. It's really huge. Once you test a specimen on the wall, you would have to really test something very large. So that's why we have finite element analysis. And there are advantages of finite element analysis because you can, first of all, analyze many, many specimens and you can create a like basically supplement experimental database with the nonlinear finite element analysis. But you have to be careful because any finite element model that you use has to be properly calibrated. And that's how we use it in my research group, nonlinear finite elements. Not really for design, but really to supplement experimental data and to create and maybe suggest design recommendations for future. Okay, so since we talk about calibration, we do have a calibrated model, which is a model calibrated in Abaqus with model for concrete called the concrete damage plasticity model. And it was calibrated on tests on slab supported on columns because we couldn't calibrate it on slab supported on walls. So there were 4 slab on rectangular columns, tested by Sagaseta and the other authors, and Mutoni was there as well in this. The next slide actually shows this, the paper. And 3 were on square columns. We used some parameters which are default in Abaqus. We used parameter which is important, dilation angle. We used tension modeling. We used compression modeling. All this slide that I'm showing here, that was a separate research which lasted a year and a half or 2 years. So I'm not going to go into details. I'm just going to tell you and hope you trust me that it was well calibrated. So next picture shows actually the response on these columns. On this bottom are the plan views of experiments that we use, and then the response is load versus deflection, finite element versus experimental data. We didn't just calibrate and check load deflection curves. We checked crack patterns and everything. So we had good view and good feeling that our model was working well. The middle slide shows, middle picture shows one slab which actually had flexural failure, and the same model was able to predict that the slab failed in flexion or in punching shear. So that's also good. So with this, we were sort of confident that we can use it now for slabs on walls. So in our slabs numerical studies on slabs on walls, we had 2 types of study: a concentric load on the wall, on the connection, and concentric load plus unbalanced moment. The reality is that most of the tests, and it's also with finite elements, it's much easier to do the concentric punching only, but in most cases you always have an unbalanced moment, so you always have a combination of the 2. We actually did a lot of this analysis. I'm just showing 3 cases here in this presentation, and the behavior of these connections is now governed by 2 parameters: beta, which is the aspect ratio, maximum size of the wall versus minimum dimension of the wall, cross-sectional dimension, and also the parameter kappa, which is the minimum dimension of the wall versus D, effective depth of the slab. So basically the thin wall or the thicker wall with respect to the thickness of the slab. And we have 3 cases. So the thin wall with kappa 0.8 around, and then 1.287 and almost 2. And for the unbalanced moment study, we only used 1, the middle one. So that one was analyzed under concentric loading up to approximately 40 and 65% of the capacity of the concentric load, and then unbalanced moment applied to the slab until failure. Okay, so how did we analyze them? Well, even in finite element, you really cannot do the full system because otherwise you would never graduate or finish or do anything. So we did create isolated slab wall specimens as if we were testing them in the lab. We had to find the radius of contraflexure. We did it with linear elastic finite element analysis. And from this system that you can see, this was our base system, we created isolated specimen and then created a finite element, 3-dimensional finite element model for the nonlinear analysis. And it was a quarter, of course, of the wall for concentric punching, but for concentric load and unbalanced moment, we had to use half of the wall because we had unbalanced moment. And this was the model, finite element model, with the boundary conditions and loads applied. So basically, the specimens were supported at the wall and loaded by the load plates at the slab, at the critical perimeter. And this was consistent with these tests that we calibrated our model on. These slabs were on columns were also tested like that. And these are some results. So here is the results of concentric load only, V study. And you can see that, well, surprise, surprise, the thicker the wall, the stiffer the connection. Well, that is not very surprising. But if you look at the crack patterns on this other side here, you can see that most of the stresses are concentrating at the tip of the wall. And you have this punching cone forming at the tip of the wall. And we also were able, this is another advantage, not only that you can replicate and augment experimental database, you can also look inside the structure to see what stresses are doing, where they are being created, where they are the maximum, where they are the minimum. And here is the profile which shows short side of the wall and long side of the wall and the stresses for the three cases of the slabs that we analyzed. You can see that all of them failed more or less at the 5 to 6 MPa stress at the corner. And you can also see how fast, this is the short side, but how fast the stresses actually go down along the length of the wall. And here is the long side of the wall, which is also very interesting. So this is the graph, and this is this detail here, enlarged. And you can see that they go very, very quickly down. Then there are basically no stresses at the sum portion. And then they are constant, which is really a one-way shear zone. So you have this concentrated two-way shear, and then you have a one-way shear. So that was good. And then we did, of course, the V plus M study, and we did this for only one case of kappa equal to 1.287. And here you have applied vertical load, and then once the vertical load was constant, we applied the moment, and up to failure. Now, the good news here is that these values are so large that none of the slabs will ever see them in real life. So that's why, and it took a lot of time to analyze just this one case under unbalanced moment. So once we did that, we thought that's enough. We don't need to analyze all of them. We can draw conclusions from this one. And these are the results in terms of stresses. Again, this is along the long side of the wall. And again, and actually I can, again, you can see this zone with no stresses. So, and also the profile of stresses at failure for both concentric load study and concentric load with unbalanced moment are basically the same. So the other reason why we didn't do any more, but just this one. I mean, we did it only for V plus M when we had unbalanced moment. That's only one case we did. Okay, so in that case, there is also the other study was done, how much load is transferred along each side of the wall, and you have a square column, rectangular, and then a wall, and you can see that more and more load is transferred along the long side of the wall with one-way shear. But if you calculate it correctly, the tips, the both toes, carry 40 to 50% of the total load, both of them. So each of them 20-25% of the load applied to the tributary area will go to these tips of the wall. Okay, so we thought we can create a design method. And this is the wall. And we thought that maybe we could do something so that commercial software packages can actually analyze these connections. This was motivated by our third author, who is consulting engineer, and he said, well, that would be good because we can't really analyze these connections. And current packages cannot handle it. So we thought maybe we can create a so-called cut wall model. So since there are no stresses in between, then why don't we just remove this portion of the wall? And we did a study, and again, I'm not showing you all these studies and all these results. We did a study, what should be this parameter and lambda and mu, so that actually the results from cut wall model and the full wall model are almost the same. So the study was done, and the dimensions are shown here. And it's actually 5D is the size of the toe. The gap is 2D. We also added slab opening because we wanted to cut the critical perimeter at that portion of the toe, because it doesn't exist there. So we added this, and this model, you have to trust me, behaved like the full wall model. So, but again, it was a whole study done. And then we proposed also, before we ran the commercial software packages, but anyway, we proposed also the design methods for these zones. First of all, we thought that we can divide this wall. The wall should be divided into a two-way shear region, toe region, and then the one-way shear region. So this is a two-way shear region where we have two design methods. One we call effective critical perimeter, and the other is linear stress distribution. In the effective critical perimeter, the toe, this is just 5D, so just the toe of the wall, you cut the critical perimeter to 2.25D, which is half, basically, and this is where the critical perimeter stops. But the stresses on critical perimeter are consistent with ACI, 0.33 square root of F prime C. This is in SI units, in Imperial would be 4 square root of F prime C. And then we had the second model, which is more realistic in terms of how stresses actually are on this critical perimeter, where we have the whole toe has a critical perimeter, except, of course, this side, which was part of the wall. Then it's no critical perimeter. And the stresses are linearly distributed in this region. And again, we calibrated all these values, what it should be, but the maximum stress is 0.33 square root of F prime C always, too much ACI code. Oh, and also I put sort of a frame over this method, because this method we actually would like to emphasize as a better one, because it's more realistic in terms of how the stresses are actually distributed on critical perimeter, and it also matches our method for rectangular column, which we published in a different paper, because our first work was on rectangular columns. This is on walls. And for one-way shear, we removed the gap, is gone, and the rest is the one-way shear region. And we actually limited the stress to 10% of 0.33 square root of F prime C, going to 15% when you have a thicker sort of wall. So when kappa goes up, then you have slightly more strength on this one-way shear region. And this is the slide which I don't expect you to memorize, but this is the whole method altogether, which is the toe region and the one-way shear. So two-way shear and one-way shear with the gap in between. So how does this compare to the finite element analysis and also to ACI? So this is just a toe two-way shear region. And the predicted capacity of the toe in finite elements, ACI, and both methods are quite comparable. Actually, the method we propose as a method 2W is more conservative than the method 1W. ACI works fine, but there is a problem. That this was done based on aspect ratio of the full wall, according to the ACI formulas. Any commercially available program, if you put them a toe, they will take the toe dimensions to predict the capacity, and then ACI overpredicts everything by 30%. So it's not very accurate. Now, if you go to one-way region, ACI is extremely conservative, assumes this is really high strength, while finite elements and proposed methods is conservative compared to finite element analysis. Really have only finite element analysis to look at. And ACI is very unconservative for one-way shear. 1 minute? Okay. Okay, so this is all together. Our proposed method is very good. Of course, ACI is very conservative. This is all combined. Oh, yeah, I have conclusions. So I'm right on time. Okay, so ACI results are unconservative when you compare to finite element method. Assumption of uniform stress along the entire critical perimeter is incorrect, but it was something we could feel. And punching shear is very unlikely to actually occur, I will just read the last one, in the absence of extremely large concentrated loads or significant slab openings in the vicinity of wall toe. So that's why these connections are really not failing, but we should know why. And for the design methods, a lot of load, 50%, is carried in the toe regions. And you can divide this wall into two-way and one-way shear regions, and we propose two design methods, and the method for designing of one-way shear region. And the method is reasonable, and if these methods were imported into the commercial programs, they would predict it correctly, because then you would have one toe region and one-way region. And so I have some acknowledgements for organizations that supported us, NSERC, University of Waterloo, and Blackwell Engineers. And I would like to finish this presentation with the slide showing that celebrations of Professor Vecchio's achievement continued. I wouldn't say that they started last year in New Orleans, but they continued already. They were in full swing last year in New Orleans. And here is Frank with his first and last PhD student. Thank you very much.